Thanks everyone for being here. I'm really glad to share some of our recent research results on how can we design more efficient markets. So this work is basically saying that, well, if we want to design a market from the scratch, what we should be doing. So we're intending to providing a framework for people to think about some of the theoretical aspects of market making. Let me start with something specific. So orange juices. So orange juice is the most popular juice in the United States. And most of the orange juices are made from concentrate. So we drink concentrated orange juice every day. And if we need orange juice, certainly we need oranges. But oranges is something that has some special features. So orange tree takes 5 to 10 years to grow, and it's very sensitive to temperature. So most of the orange juice that we use to make concentrated orange juice from just one place in the United States, so it's around Miami in Central Florida. And because orange trees are so sensitive to temperature, if the temperature drops below freezing, even for several hours, the tree can die. So in some sense, manufacturers of orange juice really worry about whether they're going to have oranges in the future to make orange juices. So as a result, we actually have orange juice futures contracts to allow people to hedge the risk. So the futures contract trades off 15,000 pounds of orange juice solid in an odd number of months. So we have contracts that will be traded in January, March, May, etc. Okay? So this type of contracts provide a way for manufacturers of orange juices to hedge their risk. So if I really worry about that in the future, I wouldn't be able to get the oranges that I need to produce the orange juice. I can try to buy some futures contract right now, such that in the future, I'm guaranteed to be able to get the oranges that I need. So that's one functionality of markets. So it will allow people to hedge their risk. Okay? But as you might imagine, because the orange trees are so sensitive to the temperature, so those people who trade in the market certainly already take into consideration of the temperature around the Central Florida area. So as a result, people did a study, and they found that the orange juice futures price can actually improve the weather forecast. So in some other sense, Marcus did an excellent job in terms of aggregating all possible informations related to the production of oranges. So that's the second functionality that I want to mention here. So in addition to risk hedging, market actually provides a very good way of getting information and aggregating those information together as reflected in the market price. Okay. So back to the theoretical model of how people think about securities market. So futures market is a type of security market. Our debut securities market is largely a theoretical model for how people can think about security market works. So if I have a state space, so what's going to happen in the future? For example, it could be tomorrow's temperature. It could be some other event. We can think about that we have a state space that contains all possible outcomes. And then we can have our debut securities, each corresponding to one state that pays off $1 if and only if the corresponding state happens. And one important notion about our debut security is what we call complete market. So what it means is if we have n state, n possible future state, and we can possibly have one our debut security corresponding to each state. So in that sense, when we have n securities, we can have a complete market. And in theory, we don't really need n because the last one can be constructed by the rest n minus 1. So the formal definition for complete market will be we only need n minus 1 linearly independent securities. If that is satisfied, we have a complete market. But complete is in what sense? So that might be the question. So the reason that we want a complete market is if we have a complete market, which is going to pay out $1 in the future when the corresponding state is realized, we can possibly using the securities to construct any future payoff in the future states. So in the sense, no matter what future payoff we want to achieve, we can use this base securities, so NON minus 1, to construct accordingly. So in that sense, if we have any possible risk that we want to hedge, these securities provide the completeness for us to hedge our risk. So that would be the great thing for financial market to have. But unfortunately, the outcome space typically is really large. So we wouldn't expect that the current financial market providing us the capability of a complete market. Okay? Prediction market is a special case of a complete market. So it's basically a financial market, but it's mainly designed for the purpose of aggregating information and generate predictions. So it doesn't differentiate itself from financial market fundamentally, but it differs in the aspect of it doesn't really care about risk hedging that much. It cares about the information aggregation functionality of markets. In a prediction market, trader trades securities, or sometimes called contracts, with payoffs associated with future event. And for example, typically they're operated as a area debut securities market. Suppose the event that I'm interested in predicting is what's going to be tomorrow's weather. And suppose that we only have 3 possible weather outcomes. It's going to be sunny, it will rain, or it's going to snow. So these 3 outcomes are mutually exclusive and exhaustive by assumption. Then I can have one security for each outcome. And basically, this is a complete market in the sense I just talked about. And if that's the case, suppose I have some information and give me the beliefs saying that, well, I believe the probability for tomorrow going to be sunny is 0.8. Then I will look at the price for this first security. And if the price currently for this security is less than 80 cents per share, then I have the incentive of buying this security because in expectation, I will make a profit. And if the current price for this security is lower than 80 cents, then I have the incentive to sell this security because in expectation, I'll make a profit. So in some sense, if everyone is doing this, then at the equilibrium, the security price can be considered as an approximate prediction about how likely tomorrow is going to be sunny. And that prediction takes into consideration of all traders' information. So that's the second functionality of a complete market. It offers the ability to aggregate information. Okay. Are we good now? Okay. So there are some examples markets that people trade securities like this. So these are all from the 2010 interest contract. For example, this security trades whether U.S. economy would go into recession or not during the year of 2010. And this is about the House of Representative control. And this is about like euros, whether any country currently using the euros will announce that they will stop using it. Okay. So this is from intrade.com. It's a real money prediction market that has been trading contracts related to a lot of political and economic events. Okay. Okay. So how does this type of markets work? We actually know very well how we can operate markets for complete markets. So if you're thinking about a complete market, we actually have fairly good mechanism to do that. So for the weather forecast prediction here, again, so we have 3 area debut securities. And then what the markets do is the market will keep track of how many shares has been purchased by all traders for each of the securities. And that's encoded by this quantity vector Q here. And the market maker keep using a cost potential function. So it uses a function that takes the input of how many shares has been purchased for each contract. And then if someone came and saying that I want to buy R bundles of the shares, so the trader can come and saying that I want to buy 10 shares of this contract and 5 shares of this contract. If the traders are doing this, then the market maker needs to tell the trader how much you need to pay me for you to get our bundles of shares here. And the total payment is the difference of this potential function. So in some sense, the cost potential function captures how much money the market maker has already collected so far, given the total number of shares that has been purchased by all participants in the market. And the difference of the cost function will give the payment that's necessary for a trader to get a certain amount of shares. Okay. And you might ask, what is the prediction here? So the prediction is given by the instantaneous price of the cost function. So the partial derivative of the cost function regarding to Qi gives the instantaneous price for a particular security here. And it's called instantaneous price because it's not price per share. You can think about this as the price per epsilon share. So how much I need to pay if I want to purchase epsilon shares or I want to sell epsilon shares, how much I'm going to get. That's going to corresponding to the instantaneous price here. Okay. And let me give an example. This is the most popular market maker mechanism that currently being used in prediction market. It's called logarithmic Marcus Garen Rule, but I'm not going to explain why we have such a name, but it's a popular one. It uses a cost function looks like this, and a price function looks like this. The exact form of the cost function and the price function is not important here. But let's take a look how it works. Okay? So supposing that I have a two-outcome market, then I have two types of securities corresponding to outcome 1 and outcome 2. What I'm plotting here is the price for outcome 1. So I'm assuming no one has purchased any security for outcome 2 so far. So I'm only plotting the price for outcome 1. So what it happens is that this is the number of outstanding shares, how many shares that traders have purchased for outcome 1. And this is the price for the first contract. Okay? And here it means that no one has purchased anything and no one has sold anything for contract 1. So we start with the price for outcome 1 to be 0.5, and correspondingly the price for outcome 2 is also 0.5. And if some trader comes in saying that I want to buy 100 shares, what it means is that this is our instantaneous price. And as people keep buying, the price keeps increasing. So the difference of the cost function is essentially this shaded area. So it's the integral of the price function. So we essentially have a continuous price function. And this red area is the total amount of money that the trader needs to pay to the market institution to get 100 shares here. Okay? And the price increased after the trader has purchased 100 shares. And now if another trader comes to the market and saying that I want to buy another 100 shares here, so which changes the quantity from 100 to 200, this blue region is the total amount that the trader needs to pay to the market maker. Okay? So that's at the high level how this type of market works. Okay? But one question we might want to ask is, well, I give you a market maker mechanism. I'm saying that the market maker offers a set of securities and uses this cost function and price function to operate the market. And one natural question to ask is this market maker reasonable? Meaning that have at least some reasonable properties that we would expect a market will have. Okay? Then let's take a look at the cost and price function. So what it means. If I look at the price for contract I, at least it's an increasing function with Qi. So this is a normalization term, so it doesn't matter. So it's an increasing function with Qi. So it means that as people keep buying the same contract, the price for the same contract increases. So this is to be expected, because if people keep buying the contract and the price drops, then people will never stop buying it. So this is actually very important in the sense of it guarantees that the price will reach to the point such that a trader will stop buying. So we would expect the price to be an increasing function of the corresponding Qi. Okay? And the second part is that if we look at this is the PI, and we sum across I, they equal to 1, right? So the sum of the prices across all possible outcomes or across all possible contracts equal to 1. And this is actually very important because we have mutually exclusive and exhaustive outcomes. And each contract pays off $1 if the corresponding outcome happens. If I'm buying 1 share for each contract, I know that in the future, I'm guaranteed to get $1 back, no matter which outcome happens. Because if I'm holding like 1 share for each outcome, there will be 1 outcome happen in the future, so I will get paid $1 in the future. And if the sum of the price doesn't equal to 1, if it's less than 1, then I can always buy in 1 share for every outcome and pay less than $1, and I know in the future I'm guaranteed to get $1, so I have a guaranteed profit there. And if the price sum to be greater than 1, similarly, I can sell equal number of shares for every outcome and I get guaranteed profit. So it means that if the prices doesn't sum to 1, we're in trouble. The market has arbitrage opportunities and may potentially be turned into a money pump. And then no one would like to operate a market like that. So this is actually also very important. And the last is just a property that this particular market have is it has bounded worst case loss. So N is the total number of outcomes, and B is the positive parameter that happens here. The market maker has a guarantee that no matter what happens in the future, the loss of the market maker is bounded by this expression. And this is a very nice property in the sense of if we want to have a market that's going to be practical, meaning there will be someone interested in running a market like that, we have to provide some worst case guarantee for the market institution. Because if it's potentially lose infinite amount of money, we couldn't expect anyone would want to use this market mechanism. So that's a nice thing associated with this market maker mechanism. Okay? Question?
So what's the typical goal of a market maker in running one of these markets?
Yeah, that's
to make some profit? Is it to get a good estimate of the probability?
That's a great question. So I guess the question is associated why the market maker might lose money. So in some sense, thinking about the market maker might lose money is reasonable is someone might want to run a market and get some information. In some sense, there might be some party who are interested in subsidize the market and are willing to lose some amount of money in order to get more accurate information. But this is also not like a hard constraint because the current setting is assuming there isn't exist any transaction fee. So if the market institution is willing to make money, the market institution can charge transaction fee. I'll also mention at the end of my talk the other ways of getting that. But there's a trade-off there. So whenever the market institution wants to charge transaction fee, it means that it's less efficient for the market in terms of aggregating information. Yeah. So this is a really weak requirement saying that I'm only requiring you to not lose money, not lose infinite amount of money.
And is there any way to quantify how quickly or the prices converge to the?
Yeah, so that's a totally different set of questions. So right now I'm only talking about like how I want to make the market and not even thinking about how the traders are going to behave in the market. And if the question is asked about like how quickly information is going to converge to the accurate or fully aggregated state, then we need to think about how traders interact with the mechanism. Yeah, there definitely work out there. Okay, so that all looks good. So when we have complete market, we know how to operate a market. We know how to use a market maker mechanism to operate a complete market, and the market actually looks reasonable. So it has some of the properties that we did there. But the challenge comes to when we have large state space, which is typically the case in the reality. So if we think about n competing candidate, then if we only restrict the things to be mutually exclusive and exhaustive, so if we're still focusing on the outcome space has to be mutually exclusive and exhaustive, what it means that each outcome will be a ranking of the n candidate. So each permutation of the n candidate will be an outcome. And then we have n factorial number of outcomes in the future, which is really large. And think about the political election example. So if we care about to predict for each state which political party will win the election or not. So for each state, it's a binary event. But think about the whole outcome space, mutually exclusive and exhaustive, then that's 2 to the power of n, all possible Boolean combinations, and not even considering the subset of those. Okay? And for the reality, if you think about the financial markets, we have options based on the stock price. And the stock price is essentially takes a continuous space. So in that particular case, we have the infinite state space. So that's the continuous stock prices. Okay? So for all these cases, we cannot naively use the market maker mechanism that was designed for complete markets. So for example, we might just think about we can run logarithmic Marcus Garen Rule, but what it means is that if we're thinking about these permutation cases, we will have n factorial mutually exclusive and exhaustive outcomes. And then we'll have to price for each of permutations. So first of all, it becomes computationally intractable to keep track of everything. So even keep tracking of the outstanding shares for each outcome. And second, humans are really not good at assessing very small probabilities. So the probabilities becomes really, really small if we have to think about at the outcome level. Alternatively, we can also think about, we can write separate market. An example will be, we can predict which houses is going to win and which is going to be like win, place, and show. That's the typical terminology in house trick racing. So win means that which one will be at the first position, place the top 2, and win and show the top 3. But if we run independent market, one for each, we essentially ignore the logical relationship between the 3 events. So if I'm betting that house A is going to win, certainly that should increase the probability for that particular candidate to be among the top 2 and among the top 3. But if we run independent markets, we essentially ignore all the possible logical dependencies among these events. Okay? So that's not satisfactory. So what we were trying to do is that we want to think about, we do have a very large or infinite state spaces, but the typical contract that we're interested in is not that large. So we're definitely not interested in predicting exactly which permutation is going to happen in the future. So for most of the cases, what people are interested in is that we might have a smaller set of securities that we're interested in offering for people to trade. And these securities are constructed based on the very large state spaces. So we want to directly design market mechanism for the smaller set of securities, and with the hope that the prices is consistent. So we don't want to run the independent markets because that ignores the logical dependency. So we want to keep the logical dependency, but we only care about a relatively smaller set of securities over the large outcome space. So that's our goal. And the key tools that we use is the convex optimization and the conjugate duality associated with convex function. David?
So to what extent are you thinking about the use of the market in designing the subset that you're going to have securitized? And to what extent are you thinking about what will somehow be natural for users when they're thinking about their beliefs?
Yeah, that's a great question. So this is all about, like, we're thinking about there might be a natural set of securities that people are interested in pricing. And that's certainly not this very large state state space. And we want to start from there without really put any constraints about like what we can do with that or what we cannot do with that. But really just to start saying that, suppose you give me a set of securities over the large outcome space. Do I have a way to tell you how a market can be run to price this set of securities without really thinking about how traders are going to interact with the mechanism? So
you're not actually asking at this point how would I decide what subset of securities I should price?
Yeah, no.
You're asking if that's given, how
Right.
do you do something?
Exactly. So the starting point is that I'm not really thinking about the trader set at all at this point. I'm just thinking about give me an arbitrary small set of securities, what a market should look like. Okay, so just let me make it clear what I mean by a smaller set of securities. So clearly we have a very large state space. So I'm representing each row corresponding to a state. But what we're thinking about is that maybe there are a relatively smaller set of securities. Suppose that I only have K securities and K is small. If that's the case, then everything I need to offer for the market to represent will be just a table menu. So what I need is that given a particular security, if some outcome happens, I can easily know what's the payoff for that security. And in particular, what it means is that we can think about that there's some easily computable function that maps to a state and an outcome to a particular a state and a security to a particular value that indicate how much this security is going to pay out in the future if the state is realized. So this is the rho function that we're talking about here. Okay? And just to get a little bit more abstract, given a state, we essentially have a vector corresponding to the payoff for all securities that I have. And I'm highlighting this because I'm actually going to use this vector. So I want to make it clear what it means. So this is this rho omega I vector that's representing, giving omega I, what's the payoff for all securities in that state. Okay? And if I have a complete market, it means I have n states and I have n securities. So I have the equal number of states and securities. And if all the securities I have are error-double securities, I will have an identity matrix. So in the sense of the complete market is a special case if we think about the menu of the securities here. Okay. Just to give some example, so think about the permutation scenario here. All possible states will be all possible permutation rankings of the competing candidates. And there's a betting language that people call subset betting that allow the traders to come up with a contract that looks like this form. So the trader can come up and saying that I pick one candidate and one position. And if what I'm claiming is that I bet that candidate A will finish at position 1. And if that event turns out to be true, this contract should pay me $1 in the future. And if that event turns out to be false, this contract is voided, so it pays me nothing. Okay? But trader can pick arbitrary candidate and arbitrary slot. And in that scenario, what we have, the securities will be in the form of a particular candidate at a particular position. And it will pay out $1 if in the final ranking, it is indeed the case that the corresponding candidate position is true. So it pays out $1 in the first two, but $0 in the last fall here for the first contract. And this actually can allow people to bet on whether I believe a particular candidate A will finish at one of the positions in the top 3 by just buying 3 contracts. A finish at 1, A finish at 2, and A finish at 3. So that's why it's called subset betting. And this has been proved to be sharply hard if we just use the existing market mechanism, the logarithmic Marcus Garen Rule, to do this type of pricing. So I think the security is already simple enough for people to think about a high-level type of betting, and it provides some intuitive way for people to express their information. But even simple things like this is already become sharply hard. Okay. And here's another example that we call the pair betting. So allow people to bet on the relative strengths of 2 candidates, saying that, well, I believe that A is going to finish ahead of B, and if that's going to be true, I want my security to pay off $1 to me. And similarly, the menu table can be constructed this way. And again, this is sharply hard if we just use the existing mechanism. Okay. So what it says is that if we only use the existing mechanism and we're trying to think about directly using the existing mechanism and figuring out what are the betting languages, so what are the type of securities we can price using the existing mechanism, we couldn't go very long because we quickly hit the complexity barrier, saying that it becomes computationally hard to do that. So what we are trying to do here is let's forget about the existing mechanism. So we want to run a market, and we don't really care whether we're using the exact same mechanism as the one that we know. What we care is whether we can have a mechanism that can achieve our goal and have good properties. And that's all where we're going. Okay. So at a high level, if we think about designing a mechanism for a set of securities, the minimum requirement is, well, if someone comes and saying that I want to buy a bundle R of securities, at some point of the market, when there has been already a sequence of purchase happen in the past, the market needs to be able to price this bundle of the securities. So designing the market is really saying that we need a pricing algorithm that can tell us how much the trader needs to pay when he wants to buy a bundle of R of securities, given the current market state is R1 through RT has already been sold by the market institution. So that's the bottom line. We need a pricing mechanism to do that, right? But the challenging question is that how can we ensure the reasonableness of the market maker? So we can always give arbitrary price. I can just throw out arbitrary numbers saying that you need to pay me $10. But if I want to operate as a market maker, I have to think about I might lose money. So what are the reasonable market mechanism that we can have? For complete market that we have already seen, the condition is really clear. So the easy argument, because we have like arrendable securities that pays out $1 when the corresponding outcome happens. So the prices of all securities have to sum to 1. But now we're not thinking about mutually exclusive and exhaustive outcomes. We're thinking about something that we call the complex securities, where whether that security pays off in the future are going to have overlapping, like regarding to the outcome space. So if that's the case, it's actually not that easy for us to reasoning what is reasonable for the market maker's pricing algorithm. So for example, if we just to think about pair betting, so supposing that I have a security that's saying that I is going to finish ahead of J, and another security saying that J is going to finish ahead of I, then clearly only one of them can be true in the future, assuming there isn't any tie, or we have a tie-breaking rule. So since only of them can be true in the future, and the security will pay out $1 if the corresponding event turns out to be true. So the prices of these two have to sum to 1. Okay. So for pair betting, we can still do some inference. But that's not enough. So this is like essentially a 2-cycle. But we can potentially have a 3-cycle. So someone saying that I is going to finish ahead of J, and then J is going to finish ahead of K, and K is going to finish ahead of I. So we essentially have a 3-cycle. And we know that at most 2 of them can be true. So the prices for these 3 securities has to be less than or equal to 2. But this really scares me because I basically wouldn't be able to try to list all the possible constraints and do the reasoning myself, because this is something that I still have some intuition about. It's pair betting, it's intuitive enough. If I have any manual of securities, I basically wouldn't be able to say what are the constraints that I need to put on the price such that my market has good properties. Okay. So what we did is we backed out and thinking about, we take an axiomatic approach to say what we need the market maker to have and say whether the property can give us some natural constraints on how we can operate the market. Okay. So the first property that we required is what we call the path independence property. So what it says is, if I want to buy a bundle R of securities, I can buy it O at a time. So I directly buy a bundle of R. O, I can buy it at multiple times, such that in aggregation, it equal to that I acquired a bundle of R. No matter how I do that, as long as the starting point and the ending point for me is the same, I require that the money that I pay to the market institution is the same. So this is essentially the path independence. And one nice thing about that is this alone actually implies that we must have a cost potential function. So we didn't really assume that the market maker will operate using a cost potential function, but we observed that when we require path independence, this naturally arises, saying that, well, if that's the case, then the payment for me to get a bundle of R shares is just the difference of this cost function. So there must exist a cost function that's doing that, such that can ensure path independence. So now I can drop this notation of cost and return to the simple notation, the C as our cost potential function. So I can actually thinking about the cost potential function based type of market making mechanism. Okay. So I have 4 other properties that I want to go through, and hopefully most of them seems natural to you. So I know that the market maker needs to use the cost function, and it's the difference of the cost function that gives the payment for a trader when a trader wants to purchase a certain number of shares. The next requirement that we have is we want there to exist an instantaneous price, meaning that it's okay for a trader to come by a fraction of shares, and it's okay for the trader to buy an arbitrary small number of shares. And if that's the case, the natural requirement is just saying that, well, this cost function must be continuous and differentiable. And we actually have a well-defined notion of price here. So the instantaneous price will be the gradient of the cost function. So this is the price vector here. Okay. So this looks a lot closer to the market maker that we had for the complete market so far. Okay. And the next property is what we call the information incorporation. So in some sense, we said that the market has a functionality of aggregating information. But traders review their information by trading in the market. So they purchase the contracts or they sell contracts to reveal their information. And our information incorporation property is actually a minimum requirement in the sense of it only requires that there's one direction for the trader to make a profit in the market. So if the trader doesn't agree with the current market state, either buying or selling is profitable for the trader, but not both. So meaning that you can only have one way to express your information. If you think the price is too low, you can buy. If you think the price is too high, you can sell. But it's impossible that we're in a very weird situation that you can either buy or sell, and both scenario makes money for you. So that's the minimum requirement, saying that we have to allow only one way for people to reveal their information in the market. And if that's the case, mathematically, what we get is that it actually requires the cost function to be a convex function. Okay. So now we have a continuous, differentiable, and convex cost function. But what's more important next is we need no arbitrage, because that's our big fear of the trader will turn the market into a money pump and constantly just getting money from the market institution. So the third property we have here is that no matter what happens, if a trader purchases a bundle R, then it's never possible that he has a guaranteed profit. So it's okay that he may make money in some state and lose money in some other state, but it's not okay if no matter which state happens, the trader has a positive profit of buying a bundle R. Okay? So that's a no arbitrage condition. And if we require no arbitrage together with the first two, what we have is actually a constraint on what the allowable price over the contract space is. Okay? So what it says is that, remember that this is a price is a gradient of the cost function. So what I have here is all possible prices. So no matter how many shares that people has purchased, so the quantity vector is just in the k-dimension real space. This is essentially all possible prices over the contract space. So it has to be contained within the convex hull of our payoff vector. Remember that when we talk about the manual of the securities, what we have is that this is the vector of the security payout when outcome 1 happens. So in the state of omega 1, so essentially the row vector in our manual table. And we have a set of row vectors, and the convex hull of the row vector is this one. So what it means is, if we want the market to not allow any arbitrage opportunity at any time of the market, then the allowable prices has to be contained within the convex hull of the payoff vectors. So we got some constraint about like what constraints we need to put on the prices. Okay? And the last one. So the last one we call the expressiveness. It's essentially saying that if I have some information that's different from what the market currently tell me, I can always change the market prices to be agree with my information. So there isn't exist any situation that I have information but I just cannot express through trading. So that's what we call the expressiveness. So the trader must always be able to set the market prices to reflect his belief. Okay? And this alone gives the other direction of this condition. So this is saying that the convex hull of the payoff vectors must be contained within the allowable prices region. Okay. So if we put everything together, now we know that, well, if we agree the 5 properties that I talked about is reasonable to require, then the market maker must satisfy this theorem, which means that the market maker must use a convex cost function, which is differentiable and continuous, such that the allowable price region is exactly equal to the convex hull of the payoff vectors. So it provides the constraint to the prices such that we can think about whether the market maker gives us the property or not. Okay? And for complete markets, it's clear that this convex hull is just the probability simplex because we have the identity matrix and every row only have 1 in one place. And the convex hull of that is the probability simplex. And now it becomes clear why we have the sum of the price must equal to 1 because the allowable price region is exactly the simplex. Okay? So far so good. We know what the requirements are. Go ahead.
Just going back to the requirements, so they're all natural, but on some, are they like, for example, the first one, path independence, and item 2 here, this information incorporation. Are they also motivated by that if those properties weren't there, there'd be some way for someone to take advantage of the market and put the market maker in trouble, or?
Yeah, so if you couple with like path independence and some other properties like the information incorporation, it also will lead to arbitrage opportunity. So in the sense of, but it's not exactly equivalent in the sense of like, if you believe that like purchasing and selling will give you the same amount of money back. So if you spend like $10 to purchase and if you sell them, it should give you $10 back. And if you believe that, and if the path independence property is not satisfied, you have a way to make money like from the market. That's essentially arbitrage opportunity. And for this one, the intuition will be, if I can both buy and sell and make a profit in the market, then I might be continuous doing that forever. So in some sense, it's also potentially hurt the market institution. But the relationship are not like a complete substitution in the sense of they're not equivalent.
I see. But then, and then 1 and 4, are those the reason are those motivated by just the goal of getting information out of the market? Or?
Yeah, I think this one in particular is motivated to like getting information of the market and also providing like the risk hedging opportunity for traders. Because if I couldn't really like express my information, it also means that I couldn't construct a future payoff that perfectly hedge my risk. So this is motivated. And this is actually really a little bit more of a technical. We just want to have like an instantaneous price that we can announce. Are there other questions? Okay, so we're here arriving this like theorem saying that if we want to operate a market based on arbitrary set of securities that's represented as a menu table, then we know that the allowable prices must be exactly the convex hull of the securities. But this is not helpful in the sense of it's not constructive. So I know that this is going to be the constraints, but how can I pick a cost function and run a market? So that's something that I'm more curious about, saying that, can you give me a cost function such that I can operate a market for this set of securities? So this leads to the question of how can we design C? We make use of the fact in convex analysis. So this is actually something well known. If I have a cost function or a function C that's closed and differentiable, then it is convex if and only if it can be written in this convex optimization form with R to be a strongly convex function. Okay. So if we look at this for a second, what it means is that if C is a convex function, this R function is the conjugate of C. So sometimes it's called the differential duality. And if C is convex, then we can always write it in terms of this optimization problem with a corresponding conjugate function. And the optimization is over the domain of the conjugate function. Okay? But what's more important is if we solve this optimization problem and get the optimal vector x star, so they are exactly the gradient of the cost function C. Okay. So remember that we said the gradient is the price, instantaneous price for us. So what it means is if we want to design a market mechanism, essentially what we need is we just need to pick a R, and we set the domain of R to be the allowable price region. And then we'll get a cost function such that we can operate the market. And the cost function is written in terms of a convex optimization. And hopefully, we can make use of techniques in optimization to efficiently solve the convex optimization. Okay. So let's take a look at for the complete market. So for complete market, what we had is essentially everything is a maximization over the probability simplex. So that's the allowable price region, and with the conjugate function. So what we have is this has to be a simplex, and this can be any strongly convex function. And if you're curious about like what's a conjugate function R for the popular logarithmic Marcus Garen Rule market maker that we saw at the beginning, it's a negative entropy for logarithmic Marcus Garen Rule. So which means that this is the cost function for logarithmic Marcus Garen Rule. It can be rewritten in terms of this optimization. So complete market is a special case for our framework. And for our complex markets, what we have is, well, we replace this to be the convex hull of the security payoffs. And again, we can pick any strongly convex function. So this gives us a framework to think about how can we come up with a cost function to be able to operate a market based on the set of securities that we're interested in, while the outcome space can be large. Okay. So the nice thing about thinking about market making in this framework is some interesting properties also related to this conjugate function R. So for the logarithmic Marcus Garen Rule market maker, we know that the market maker has bounded worst case loss. But for the framework that I have been talking about so far, I only derived according to the 5 properties, which doesn't directly touches about the market maker's potential loss. And the market maker's potential loss is something that we actually think very important to consider, because if the market maker can lose infinite amount of money, no one will be interested in using the mechanism. It turns out the worst case loss of the market maker can be expressed in terms of the conjugate function too. So this is basically the over the domain of R, the maximum value minus the minimum value of R. So it's like how widely spread this R function is over the domain represents the market maker's worst case loss. And we can also think about some informational properties of the market maker, which I'm not going to talk in detail here, which is also related to the conjugate function and have a precise expression in terms of R. Okay. So it means that if we think about the conjugate function, it gives us a way to think about the trade-offs of designing a market. So I may want the information loss to be smaller, and I'm willing to provide more money to incur a larger worst-case loss as a subsidy to the market. So it provides some trade-off in terms of designing the market. Okay. So that's the general framework. Any questions so far? We good? Okay. Now I'm going to give a few specific examples showing that the market maker mechanism that we used before, designed for complete market, couldn't really handle subset betting and pair betting. But now within this framework, we actually can handle some of them. So this is for the subset betting. So for subset betting, the traders essentially place bets in the form of whether candidate I will finish in a position J or not. And it will pay out if in the final permutation, I is actually located at position J. So it will pay out $1 if that indeed is the case, and $0 otherwise. Okay? So what we're interested in saying is, what's the security payoff corresponding to a particular outcome, right? So that's the row vector. But here we can realize that actually given a permutation pi, the security payoff can be easily represented as a matrix. So instead of saying anything in terms of a row vector, so it can be represented as a matrix. And the matrix is essentially saying that, well, if I finishes at J according to the permutation, this is going to be payoff $1. And then the allowable prices that we need to pick or we need to define is the convex hull of all these type of payoff matrices. So there are 2 things that we need to decide. So one is the domain of the R function, and the other is the exact R function, which one we want to pick, right? So regarding to the domain, it's the convex hull of this payoff matrix. And this is a known result that the convex hull of this type of payoff matrix is just the doubly stochastic matrix, meaning that every row sum to 1 and every column sum to 1. And the nice thing about it is we actually don't need a lot of constraints to represent the convex hull. So we need a relatively small number of constraints to be able to represent the convex hull for this type of payoff matrix. And since we don't need a lot of constraints and we have a convex optimization problem, the problem is computationally easy to solve. So now we just need to pick a conjugate function. So this is just analogous to the negative entropy function, but since we don't have the probability distribution x here, so this is not exactly the negative entropy. But if we pick this conjugate function, we essentially have a market maker mechanism that can operate for subset betting. And the worst case loss of the market maker is this lambda is a positive parameter that we can adjust. So this is lambda times n log n. And I want to mention one thing. When we use logarithmic Marcus Garen rules for one market, the worst case loss will be lambda times log n for one market. So this is essentially almost like that we have the worst case loss for running n independent market. So we're considering the whole n factorial outcome space. Okay. So that's one example. So the second example is kind of a cheating.
That also seems to match what, if you view it as a complete market with n factorial outcomes as like log of n factorial.
Yeah, so if we run it as a complete market, so even if we ignore the computational difficulty that we have, assuming that we can compute the price, the worst case loss will be lambda times log n factorial here, so which is potentially going to be really large.
Oh, it's about the same as that.
Is that the same?
Yeah.
Okay. Okay. That's good. I thought it's actually a lot smaller because when you have one independent market, you have lambda times log n, but you might be right. Yeah.
Confused about.
Okay. Okay, so I have another example because I keep saying that it can work for continuous space too. So I want to give an example for continuous space. But this is a bit cheating in the sense of like it's not really a combinatorial market in the sense of the computational part is really hard. It's more or less like that we don't know how to put constraints for the market. So let me explain that. This is an artificial example. So supposing that we have a satellite is circling around the Earth. And what we're interested in predicting is the landing location of the satellite on the Earth. So what we have is, we believe the location on the Earth as a unit vector here can be represented as a unit vector in the 3 dimension. So essentially x, y, and z coordinates. Okay. And what we're doing is we want to predict the landing location on Earth of this satellite. And the payoff is essentially corresponding to the x, y, and z coordinate of the landing location. So what we have is we offer 3 securities, each corresponding to 1 coordinate. And if the satellite falls at a particular location in u vector, then security I pays off ui plus 1. So plus 1 is completely unnecessary. So what I'm doing is I just want to shift everything in the positive coordinate, rather than thinking about like things can be in the negative coordinate. So this is completely unnecessary. What it says is that if we look at the 3 coordinate, what we're trying to predict is the expected value along that direction, and we will pay according to that.
Why are we using, we're only thinking about the surface of the Earth.
You can think about the surface.
So is there a particular reason to use 3 coordinates rather than 2?
If we think about the surface of the sphere, we still have the 3 directions to go. So if you think about the unit ball, does that make sense?
Seems like we should be able to represent everything just latitude and longitude.
Yeah, so that's a great question. So I believe you can do that. So essentially there's a 1-to-1 correspondence of like this type of representation and the 2-dimensional representation that you have to representing the spherical space. I believe you can do that. But it's not clear how you're going to pay off in that space. So constructing the contract is a little bit tricky. You have to go through the mapping from this space to that space. So that's the caveat here. Okay. So if that's the case, then we can offer securities like this to predicting the landing location. And let me do a comparison. So if we're considering a cube, and the object can actually fall into inside of the cube, then we don't really have any difficulty here because we can just run 3 independent markets. So we can have 3 markets, each corresponding to 1 coordinate, and the landing location can be any point within and on the surface of the cube. So if that's our problem here, we don't really have any difficulty. But the tricky part here is that we have a sphere here. We have a unit ball, essentially. And unibound means that some of the points are not possible to be achieved. So we have some natural constraint enforced by the unit bound that we have to have our market to take into consideration. So in that case, we know that the convex hull of our payoff is essentially the unit bound centered at 1. So we think about the Earth as a unit bound, and we shift it to the positive quadrant by adding the 1 here. And unit bound is easy to represent. And we can just pick a quadratic, like the square of 2 norm conjugate function. And then we'll have our cost function being represented in this form. And we can run our market. And the worst case loss of the market maker is just this parameter lambda that we used here. Okay. So that's fair betting. And how about pair betting? So I said that is also sharply hard when we use the logarithmic Marcus Garen rule. So we revisited pair betting in our framework, but unfortunately, representing the convex hull of pair betting is not computationally efficient. It can be reduced to the minimum feedback arc set problem. So it means that if we can actually price pair betting efficiently in our framework, which will mean that we can solve this computationally hard problem. Okay. But this is not the end. We actually have hope for this type of thing. So we have the computational complexity kicks in again, saying that you wouldn't be able to operate a market efficiently. But what about the properties that we have considered before? So I start with 5 properties. Are all those properties necessary? So essentially, our axioms implies that the feasible price region must be exactly the same as the convex hull of our security payoffs. So this must exactly be the same. Is this all necessary? So it seems to be necessary in the sense of, while it guarantees that there isn't any arbitrage opportunities, it also guarantees that people can always express their information in the market. But if I step back for a little bit and think about, as a market maker, do I really care about there isn't any arbitrage opportunity at any point of the market? Because sometimes it seems to be reasonable if some trader just comes into the market and creates the arbitrage opportunities, it's fine for the market institution because it doesn't cost the market institution money as long as the arbitrage opportunity is taken care of by other trader or even by the market institution per se. So it also seems to be what we care is not to enforce at any particular time there are not allowed to be arbitrage opportunity. What we care more about is the arbitrage opportunity doesn't cost the market maker infinite amount of money. So that's what we care more. So if you look at this closely, so suppose we only have this direction. So this means that this is the expressive, this means that we relax the expressiveness. It turns out the market maker's loss will be unbounded. So this direction is crucial for us. But the other direction is fine. So if we relax this direction, so we only require this one, the convex hull to be within the feasible price region, it implies that our no arbitrage condition is no longer satisfied. But as long as the market maker starts with some initial price that's within the convex hull, it doesn't affect the worst case loss of the market maker at all. Actually, it can only improve the market maker's worst case loss. So that means we can again think about the problem as having a cost function, running a convex optimization, but now we don't require the domain of the optimization problem to be exactly the convex hull because sometimes it can be computationally hard to represent. We can relax it to be something bigger than that. And if that's the case, we can deal with the pair betting. So we can just come up with some natural constraints for pair betting. And since we have a relatively small number of constraints here, we can operate the pair betting market computationally efficient. Danny?
Is the intuition there that you only care about somehow arbitrage on a path? Because I guess even if the no arbitrage condition fails at a point price, as I trade, the price moves.
Mm-hmm.
Right? It seems like the arbitrages play now, do they basically pull the prices back into the hole?
Yeah, so that's a great. Can I answer a second question first? Because I wasn't sure that I have a satisfactory answer to your first question. So, so what does this mean when we do the relaxation? So for complete market, it's actually very intuitive because if we don't allow any arbitrage opportunity for complete market, the prices are required to be summed to 1. And when we do the relaxation, the prices can sum to be greater than 1 at some point of the market, which is essentially saying that if someone is buying 1 share for each contract, the market maker is collecting more than $1, and in the future only pay out for $1. So that's how it's outside. So as long as the price vector is within the convex hull, we don't have arbitrage opportunity. And the idea of get rid of the arbitrage opportunity from the market maker side is if the market maker starts with some initial price vector that's within the convex hull, it actually allows the traders to move it outside of the convex hull and creating some arbitrage opportunity. And that opportunity can be taken care of by other traders who figure out that there exists some arbitrage opportunity. Or if it's computationally easy for the market maker to do that, the market maker can also correct that. So I think I didn't really answer your first question. Okay, so the last point that I want to mention is, so the relaxation not only help us to deal with computational complexity issues, sometimes we might want to have this type of relaxation because as I mentioned that if the market maker is interested in imposing some transaction fee, this is a natural way for the market maker to impose transaction fees because it allows the market maker to make more money as the transaction goes. So sometimes this is even desirable for us to do this. And I also think about this as doing relaxation as a way of approximate the exact pricing for combinatorial markets. Because typically the worry is if we cannot provide the exact pricing for the contracts in the market, doing approximation might be dangerous because the approximation essentially means that potentially there might be arbitrage in the table. But in this framework, if we're doing relaxation of the convex hull, the guarantee is, yes, we are creating arbitrage opportunity on the table, but in a way that it doesn't really hurt the market institution's worst case loss. So it's still safe for the market institution to run the market in this way. I think that's everything I want to say. I'll be happy to answer any questions. So.
So I understand a little bit more about how one thinks about arbitrage. So all these, the constraints that you put in and then removed one at the end refer to kind of arbitrage within the market that I'm running as a market maker.
Right.
Does one also worry about arbitrage between
Across markets?
Yeah,
that's a great question. So in some sense, this framework doesn't worry about that because it's essentially built on, we can consider the exponentially large outcome space, assuming that you can take into consideration of everything as the outcome space, and then we operate a relatively smaller number of securities. So this framework really doesn't worry about that. But in practice, I think even if we can do this, we probably wouldn't be able to take into consideration of all possible outcomes. So that's a natural question to ask. If we have separate markets, and so even this framework couldn't deal with a really large outcome space, we have to separate them out. And how can we deal with the arbitrage opportunities? So I think the motivation of doing this type of research is, if we think about the current financial markets, it's designed hundreds of years ago for human beings to perform the operation. And now, as the computer technology advanced, the computers mimic the operations of the humans. The underlying mechanism hasn't been changed. The underlying mechanism is still really, really simple, but it's just the computers are doing the same operation as what humans used to be doing. And as a result, we have a lot of simple independent markets. and hedge fund and other people are trying to make profit by exploiting the price inconsistency. So the whole model just seems to be not the ideal, because you have really, really simple mechanism and you allow very complicated techniques of exploiting the arbitrage opportunities. So why not start with more efficient mechanism? David?
So are people also looking at asking whether somehow it's an intractable problem for people to manipulate the arbitrage opportunities, and would that then be the adequate ultimately to like the
Yeah.
no arbitrage opportunity?
Yeah, that's a great question. So I think that's orthogonal direction that's very interesting to explore to this compared to this work is we worry about arbitrage opportunity a lot, and if the market cannot operate, so if the market maker cannot provide the pricing such that it's always consistent and prevent arbitrage opportunity, maybe in practice it's okay if finding the arbitrage opportunity is computationally hard. And people haven't really looked into that direction that much, because it's intuitively the difficulty will be it requires assumptions about how other traders are going to behave in the market, and if you have really dumb traders in the market, there always exist arbitrage opportunities. Yeah. I think it's a connection between when arbitrage opportunity going to hurt the market institution. That's really important, because if it doesn't hurt the market institution, even it's simple for traders to figure it out, it's probably okay.
Unless it begins to lead to a participation problem, because
Right.
people begin to view it as unfair.
Exactly. Yeah. Right. So there's totally the other side of the market of even if we have this type of mechanism, how the trader is going to perceive and they're going to interact with this mechanism is an interesting question to start in. Alice?
So you mentioned there will be information loss measured by the bid-ask spread.
Yeah.
So I thought for a complete market you don't have a bid-ask spread.
Yeah, that's a good question. So let me go back to, I probably shouldn't do this. Let me go back to this slide. So what I mean by saying the bid and ask spread is, if you think about the way that we operate the market, it's a continuous price function. So at any particular point, the instantaneous price is the price per share when you buy epsilon shares or you sell epsilon shares. So which is the same. So buying or selling an extremely small number of shares, the cost is approximately the same. So in that sense, it doesn't seem to be a natural bid-ask spread here. But this really doesn't mean that there doesn't exist a bid-ask spread, because the bid-ask spread means that the difference between the cost for me to buy some shares minus the payment I will receive when I sell some shares. And if the natural restriction, you can only buy shares in unit of 1, is restricted here, then buying 1 share versus selling 1 share, there's a difference. So buying 1 share is more expensive than selling 1 share. So there is the bid and ask spread. And the trade-off here is actually, if the price function is more steep, it changes quickly. It means that you will have a larger bid and ask spread. When it's more flat, the bid and ask spread is smaller.
You said something about if you added transaction costs, it changes things. Does that help you with arbitrage as well? Because suddenly it's not as a good idea.
Right. So there's 2 ways of thinking about adding transaction cost. So the typical way is how the stock market is currently operated is for every transaction, the market institution charge you a fixed amount. So that essentially increases the cost of participation. Because if my potential profit is I believe I can only make $5 out of this transaction, but you charge me $7 as the transaction fee, then I will not participate. That's essentially the part. And that doesn't really relate it to arbitrage. But the way that I talk at the end is relaxing the convex hull, so allowing the prices to go outside of the convex hull. That can be perceived as charging transaction cost from the market maker's perspective, but it's different in the sense of like the transaction cost is not associated with any particular contract, because what I have is just the sum of the prices will be greater than 1 for a complete market, in the sense of in aggregation, I'm getting more money than I should be, but I couldn't really decompose the extra money for every contract. I couldn't say that I'm charging this amount of money as a transaction cost for this contract. And that will affect the arbitrage opportunity. That essentially saying that sometime in the future, the market will exist some arbitrage opportunity, but other traders can take care of that.